Hi class. This week we are dealing with atomic spectra. This goes with chapter 8. By now you should have already started reading this chapter. If you have not, I suggest you tackle the lectures and reading the chapter before you start the slab, or the slab will be fairly confusing, even though it's pretty straightforward and probably um, in my eyes a little easier than some of the other labs to do. If you contact me asking me for help, I'm going to tell you where you can find the information. I'm not going to handhold. I will determine how much you have actually done. Will not just provide answers. I have no problem helping students, but I'm not going to just give answers, especially when you see that I've actually given you some information on this lab. I'm going to, some of these slides, if you've already started watching lecture, you'll see that some of my slides are taken from the lecture already posted. So I am assuming that students, or I am stating that you should start tackling this chapter before you do the slab. I'm not starting from ground zero. There's an assumption that you have already started this. Light energy. Light is a form of energy that can be described as a moving wave. We are interested in the visible light, and that's where we're going to pick up with this lab. Light can be refracted, direction changed, it's a fancy word, through a prism. Properties of light. The key thing you need to understand here, wavelength and frequency. Wavelength is this little upside down kind of V. It's lambda, and it is in meters. And when we're discussing visible, we use nanometers. But when we plug it into equations, we use meters. Frequency is nu, it's this little fancy V, and wavelength, as you can see here, wavelength and frequency are inversely proportional. So what that means is that if one goes up, the other goes down. If I double one, then I have to have the other one. Why is that? Because when we plug it into this equation, it is frequency times wavelength equals the speed of light. The speed of light is always equal to a certain value. So in order to attain that, one must go up and the other value must go down to keep this with that value. Electromagnetic radiation, a spectrum, radiation. Here is some key things I want to point out. I told you that frequency and wavelength are inversely proportional. So when you have a long wavelength, you have a low frequency. When you have a short wavelength, you have a high frequency. If you go down to the bottom, we have energy. A low frequency equals a low energy, and a high frequency equals a high energy. So what I'm trying to point out here is that frequency and energy are proportional. So if you have a high frequency, you also have a high energy. If you double one, you also have to double the other one. Now, we normally use nanometers when we're using visible because using these long exponents makes it difficult. But in some cases, you can still use them. Depending on wavelength, you can easily take a value and see where it fits in here as well as in here. Energy, this is the high side, so you have gamma. Let's start with visible. It's easier this way. Visible is what we're going to use for the slab. Infrared is on the lower end, and ultraviolet is on the higher end. Red is on the lower side of energy, and violet is on the higher side of energy. So red here towards infrared, and ultraviolet sides with violet, which is on the higher energy of the visible spectrum. Here's just another, like I said, some of these ranges are really fancy. Some go to 350, some 750. We're just going to say 400 to 700, but I wanted you to still see this. This is straight from your lab. I pulled this off the PDF. So you can see they're using 750 to 400. We're going to use 400 to 700 and leave it at that. Wave particle duality of light. So we can explain light is able to function as a particle and a wave. Why is this? Because when experiments were conducted, using light as a wave was not able to explain some of the behavior that they were able to see based on the results. So there is another portion of this that is particles of light. They're photons. They are not, one portion of this is not better than the other. Both work together to explain the results that we're able to obtain. And by having the wave particle duality of light, everything is explained perfectly and it all makes sense. Sometimes we use wavelength, Other times we use particle, and we are able to explain what we are seeing. How do electrons jump into a higher orbit? Well, this is where photons come in instead of wave. Photons are particles of light of energy with no mass. To excite an electron, it will take up one photon. Depending on how far it's going to jump, that's specific, more specific than what I'm trying to explain here. But an absorption is an incoming photon is absorbed by the atom. It will jump up depending on the energy that that photon will give that ground state electron. Now, electrons will not become excited unless there's a specific value that it can cause it to excite. So meaning no random photon is just going to cause it to become excited. It has to have a specific energy value for that to happen. If not, it's just going to pass right through with nothing happening. So an absorption is when the electron becomes excited. It will be an excited state by jumping to another orbital. In lab flow, they call it electronic transition. Energy level is the easiest way to understand it, but there's several terms here. So lab flow calls it electronic transition. Eventually, the electron will have to go back down to the ground state. And when it does, if that energy that it took in is when it's emitted is in the visible wavelength, then you'll see a color with that happening. And it will be the exact same value, numerical value, that the electron accepted as an absorption to become excited. It will release that exact amount of value to go back to the ground state. So that's what you see here. This is an electron that would be emitting energy. And when it does, or a photon, if it's in the visible wavelength, you're going to see a color. These are just more visuals and some terminology. Ground state is the lowest energy state. It's the most stable, where electrons will be. Excitation, when an electron jumps from a lower energy level to a higher energy level by absorbing, that's the key thing, absorbing energy from light or electricity. Emission, when an electron relaxes from a higher energy level to a lower energy level, results in the release of an energy as a photon, one photon. And if it's several levels, then there'll be a photon depending on if it breaks up. For instance, if it goes from 4 to 1 without any distractions or disturbances, it's one photon. But if it breaks into separate levels, there's a photon for every level. From 4 to 3, 3 to 2, 2 to 1. This is when I was talking about colors being given off in the visible wavelength. This is a nice example of that. You don't need to worry about these colors or these fancy names, but you can see when there's emission for a hydrogen atom, there are spectral lines that go with the hydrogen atom. So these obtained here can tell you the transitions that occur with the hydrogen atom to give off these colors. This is a fingerprint. Hydrogen atom will only give off these spectral lines in these specific wavelengths. No other element will do this, so it's a fingerprint for this element, and every element will have its own spectral line, so every element will have its own fingerprint. Energy and frequency. Again, this is another slide from the lecture I posted up. Low energy photons, when I discuss, let's go back. Energy and frequency are proportional to each other. It's very easy to see here. This is energy. This really means energy of one photon, but we don't write the photon out. This is Planck's constant. There's a little fancy line here, but most just put it as an H. And then frequency is a little fancy V, but it's not here like that. Anyways, H is Planck's constant, and energy is in joules, and frequency is 1 over S. So if everything here is done correctly and you want energy, you can see here joules is, for Planck's constant is joules times seconds, and frequency is 1 over seconds. The seconds will cancel out, and energy of a photon will be in joules. It's very important that when you understand equations, you understand the units that go with them. The more that you understand what units, you can break down word problems easier, because sometimes things are not stated clearly. We all know chemistry is a whole different language. So the more information you have going in, the easier it is to understand what needs to be done. So if you understand energy is for one photon, even though it's not specifically stated like that, that's what this means. It's in joules. Planck's constant is joules times seconds, and frequency is 1 over S or hertz. Then we go here back to frequency. Frequency times wavelength equals the speed of light. Frequency doesn't change. It's 1 over s. Wavelength is meters, and speed of light is meters per second. So when one cancels out, the other unit will still be left over. Why am I bringing these both up? Because you can actually use them together. Now, in my problem set with my student sessions, I actually don't do this equations this way because your book doesn't show them this way. So I worked out certain problems, including this problem, but I did it in 2 steps. I calculated the frequency, and then I plugged in the frequency for the second equation. Here, they are providing it in 1 step. I don't normally show shortcuts, but your lab flow is showing this. So because it is, I am now going to show you how to use it, but your book doesn't show this. So that's why I kind of stayed away from it, because you have no reference for it. One type of sunburn occurs through exposure to UV light of wavelength of 325 nanometers. What is the energy of a photon for this wavelength? This is where, if you don't understand what's going on, the more you understand with equations and units, you instantly know what needs to be done. Keywords here: energy. We have an E. Photon. When it's a photon, you are using the equation E equals H times frequency. But it's asking for wavelength, and we have a wavelength here. So we are putting these together. How are we putting it together? Well, frequency ties both these equations together. So if you isolate for frequency, you can have c over the speed of light over wavelength. Plug that in where frequency is, and you can do this all in 1 step. That's easier than me doing 2 steps, but I tend to do the 2 steps because your book, again, doesn't show this very clearly. So you have Planck's constant. You can plug that in. You have the speed of light, and then you have your wavelength that has been converted from nanometers to meters, and it should always be in meters when you're using it for equations. You need to have the same units to have things cancel out. Since this is energy, my answer should be in joules, and it is. What if I wanted to determine a wavelength from an energy? What wavelength of radiation has an energy of 2.87 times 10 to the negative 18 joules? Same thing. You use the same equation. Now you're going to flip these. Energy is going to go down here. Wavelength is going to go at the top. You can plug everything in, and you can get meters, or if the question asks for nanometers, you can solve for the wavelength. Why am I showing these? Here's a hint. They might be in the quiz portion and in the actual lab report that you'll need to solve for some calculations. Now we are getting into wavelengths of visible light. Here we go. I told you it gets real fancy. This one's saying 750. This says 380, but the other one over there on the previous slide said 350, or was it 750? Doesn't matter. We're just going to cut it off at 400 to 700 like this one says, and make it as easy as possible with those numbers instead of trying to remember different numbers for every picture that's shown. You should pay attention to certain things. The smaller the number is, the higher the energy, because that is the smaller frequency. The larger the number is the lowest energy. Those are the largest wavelengths for visible. So this would be more on the UV side. This would be more on the IR side partnering next to it. A spectroscope. I'm not going to really go into this too much because, yes, this lab talks about spectroscope, but it doesn't really focus on it in this. A spectroscope is an instrument that allows scientists to determine the chemical makeup of visible source light. So if you were doing this in a lab, you would have a little handheld one, and you would be looking at a fluorescent light, incandescent light bulb, and so forth in order to make your determinations. This is just a quick overview. You can pretty much see with the visual of what's going on. You have a light source, goes through, separates the different colors of light, and you have a white light, this entire visible light spectrum. Sorry, I'm talking too fast when I get tongue-tied. Depending on what kind of instrument, you can determine spectral lines. An atomic spectrum is a spectrum made from a group of colored lines that are formed when atoms become excited and emit light. So what does this mean? This, I'm going to go through this in a little bit, but if you have black lines for this instrument, that means absorption. These lines are actually missing. That's why they're black. This is an excitement, this is an absorption. Then they become, eventually what comes up must come down. So then they are emitted. And when they are emitted in the same exact lines that were taken from the black lines. So here's more continuing to make it understood. These black lines here are shown that these are elements or an element, atoms that were absorbed, so they are missing from the spectrum. But eventually there's an emission, and these lines will dictate what these elements are. So here is, actually this one doesn't show absorption. This one does. Emission. This is showing the lines that were absorbed and missing from the spectrum. I'll go more into that right now. What is a spectral line? A spectral line is a dark or bright line in otherwise uniform and continuous spectrum, resulting from the emission or absorption of light in a narrow frequency range. So I'm going to show you, you can visually see when things are either going up or coming down. They give off certain colors. Each type of atom has its own unique pattern, so this is a fingerprint. This means that each type of atom shows its unique set of spectral lines produced by electrons moving between its unique set of orbits. This picture here is figure 0.5, I believe, and this is the sun. So it's showing elements that were absorbed that have been on the outer layer of the sun. Absorption spectra. The exact wavelengths of light given off by an atom of particular element when it releases energy are also the same wavelengths those same atoms are able to absorb. So it's that energy that absorbed and energy that is removed should be the same values. And when the energy is emitted, it shows us colors. When it's absorbed, if you're looking at a line spectrum, you'll only see black lines because those lines have been absorbed. So those wavelengths have been absorbed, they're missing. Atomic spectral line. So here's a perfect example of a hydrogen absorption spectrum. You can see the black lines are where this has been absorbed, these lines for hydrogen. And then eventually there's an emission spectrum where the exact spots, values, these wavelengths, show the emission from the energies. This one doesn't show too clearly, but if you look down here, you can see that there's a really thick red line compared to the others. The lines that are thicker have the most intensity. So that's the one that pretty much is defined more than the other ones for that element. The black lines indicate where the wavelengths of specific energies are absorbed by atoms. They're missing from the spectrum, and then they eventually show up. And you can see here where they can break it down with the actual values of nanometers to determine what this element would be. There's another type of spectrum called continuous. It's produced by solids, liquids, and dense gases to produce no gaps. So you don't see any gaps. It's continuous on here, and you can see here too, that's just continuous of wavelength of light produced. Sometimes a substance that is heated will produce a continuous spectrum. A continuous spectrum is all the colors of the rainbow and all the different shades of colors that can be produced. So the sun and incandescent light bulbs produce a continuous spectrum. And I apologize, this is kind of blurry. I think I enlarged it too much. Oh, this is just the same page. I messed this up right here, so I didn't realize I made a copy of it. This is fluorescent. It doesn't matter. Fluorescent lighting shows you actual spectrum, and something that's an incandescent light bulb does not. So this is different. Fluorescent will show an exact discrete wavelengths. An incandescent light bulb shows you just a continuous, which is a part of your lab, so this isn't too bad. Here's just some more enlargement of it. I put fluorescent so you can see that goes with this one. This one would be a light bulb, incandescent. Okay, so now we're going to get into your lab. This is not a difficult lab. It's different than the other labs that you've had. There is nothing being entered onto the data report. You are actually going to print out your PDF. You're going to complete the pages that I'm requesting, and I'm not requesting all of them. And you're going to upload it, and that's it. There's nothing being entered, just an upload. I'm going to show you where you're going to get your information from. But part A, you are looking at a fluorescent light. This would be, or what you should see, in a series of separate colored bands. So this is what you would see. And this is from a PDF that's also being supplied with all your samples in it, which I'll show you where to get that. Here is your experiment PDF that you're going to actually have to use, and you're going to upload. Draw the emission spectrum on the report sheet at the relative positions of each band on the scale. Label the color of the bands, or use colored pencils. Use the scale, estimate the wavelength of each band. So you're going to actually have to do a calculation with this. What you're going to do is you're going to see this picture. I just enlarged it, but I'll show you where it's at. And you're going to copy these down with colored pencils, pen, or highlight, and to tell me where these are. So you do your best to match these up as best as possible. Do you have to do all of them? You have to do the most prominent ones. You definitely have to show enough to that you actually worked on this. And then once you can figure out certain things, part of your lab is asking you to do some calculations. Here's a hint. I've given you some calculation problems, sample problems that should help you determine how to get this information that it's asking for, which is going to be some energies. So this is a spectral lines for a fluorescent light. Second one, incandescent light bulb. This is a continuous. Here you are looking at an incandescent light that would be in a desk lamp. Looking at white light contains every possible wavelength of the visible range. Use pencils, draw, sketch the emission on a report sheet that represents what you see. Now here it looks like a ruler. Just keep in mind these are in the hundreds and they are in nanometers for all of these. So just make sure you understand that. Part B. Part B deals with gases discharge lamps. Again, all these, I'm going to show you where you're going to get all this stuff. It's on a PDF and all the samples are on 2 or 3 pages. You just got to go through and they're labeled pretty decently. Again, I took a picture from your experiment PDF. Here is what it is. Same thing. This is nanometers. It's not a ruler in the sense that we understand it. This is in hundreds. And you're going to try to match it with what you can see here. Excuse me. You're going to view the emission spectrum of each gas of the discharge lamps. When viewing the spectra of the discharge lamps, the scale positions and the color of all the bands are recorded. So you can see there's prominent ones here, and you're going to do the same. You're going to draw out the prominent ones and where you see them on the wavelengths as best as you can. So there's helium, there's neon. Some of these get a lot more complicated, but you can do your best. And krypton, same thing. So considering the fact that you're not actually doing data, you're not entering data into it, you're doing an upload, this is not difficult. All right, and then we go to part C. I believe that some of you in Chem 10 actually did a portion of this lab. This is a fun lab because this is how you can see what the colors of fireworks. The metal cations are what give the colors off. You are going to follow proper procedures that are pretty easy to understand in your instructions, which I'm not covering, but I'll simplify it. You're going to have a metal wire. In the other college I'm at, I think they use a platinum wire. And what you do is you dip it in solutions and then you heat it. And you can see colors. And you can see here, there's very pretty colors. Some of these colors are very fast to go away. Like in a blink of an eye, they go away. You sometimes even question if you saw it. And then others stay for quite a while. In fact, they can mess up your other stuff by being impure because, like, for instance, copper takes forever to go away. And when you're trying to do another solution, you have a hard time getting rid of that color, even though you're supposed to clean your wire between every trial. So let's say you clean your wire and you dip the solution in lithium chloride. You see the colors, you're done. You dip it back into the cleaning solution and you do this until you see no red, and then you go on to the next one. However, copper doesn't like to go away. So I always tell my students to do copper last. It's one that just doesn't like to, it likes to stick around. Potassium, very, very quick. You can lose the color in a blink of an eye. It's that fast. Where something like copper can stay for quite a while before it actually disappears. So some of these have all of these have different time values of how long they actually last, but they're all seconds. They don't really last that long. So this is actually a nice lab to do in person. It's the only lab that's really colorful. Um, I do this with most of my classes, so it's too bad that you guys couldn't be in class to do this. And then I've never done activated charcoal, but this is actually a part of this lab, and this is a picture that I believe they've given into the PDF of what activated charcoal would be, where you would dip it into charcoal powder and then heat it up. This is what LabFlow gave you guys on the PDF. Do you see any problems with this? They all look pretty much the same on the top row. I found this, which is much nicer and prettier, and you can definitely see the differences because these are both red, but you can see one's brighter and one's darker than the other. These are both orange yellow. And you can see one's brighter and one's not. And same barium chloride. It's kind of a weird color here. So anyways, you see, this is what they give you to write up. This is what I'm giving you to write up. Use this one and not the PDF with these. These are horrible. They should, I'm not going to say anything. Anyways, where is this information at? You have a PDF. So along with the experimental PDF that's right here on this side that I didn't copy, you have a sample data. This is a PDF data, I think I said. Um, this is a PDF. It's a couple pages long, and it's very designated into each section, and it's just giving you pictures that I've already put up here for each section to help you. So there's really no experiment. You're looking at pictures, you're drawing what it is, and then you're uploading. And that's what it says right here, file upload. There is nothing more you're doing on this report except for answering questions. Now be careful. The lab is specifically asking for certain calculations on certain parts. I want that done. It needs to be clear. If you don't show me the calculations, you're not going to get the credit you're expecting to get. I want everything to show that an effort was made on here, because it's really easy to enter on the internet, but I want to actually see calculations with units the proper way it would be. Carry everything over. Now, this might seem a little confusing, so feel free to email me if you need to, but really it shouldn't be. In your atomic spectra, the PDF, experimental PDF, there are pre-lab questions. I don't want the pre-lab questions. Don't give me those. There are post-lab questions. I don't want the post-lab questions. Those are yours. The actual report, the lab report, starts at page 8. Page 8, page 9, page 10 only. So there's 3 pages I want. That covers part A, part B, and part C. Now, there are 3 questions involved in between these sections or close to each other. You have questions 1, 2, and 3. I don't care about 3. It's at the bottom of page 10. You do not have to answer it. And if you do, that's fine, but you're not going to get extra credit. I do expect you to answer questions 1 and 2. So this is not a lot of work compared to what you guys have done in the past. Complete 8, 9, and 10. There are calculations. I have put up sample problems to help you understand how to do that. And then answer questions 1 and 2. Do not upload your pre-lab. Do not upload your post-lab. There are other questions. I don't want any of these. 3, 4, 5, and 6. You are expected and should answer questions 1 or 2. I will be reading all of these, and I'll expect proper, clean, clear work with calculations. Complete and clear sentences. So one words are not going to get you. You're going to be surprised, and I'm going to deduct points. You're not going to get points if you give me 1 or 2 words, unless it's a sentence. I want a clear, proper sentence. Complete and clear sentences where applicable, partial credit if this is not met, or no credit. Deductions for not following my directions. What is that? Don't upload everything. Give me what I'm asking for. Must provide and answer the things that I'm asking you to answer. If you leave a blank, you're not getting credit. Must provide clear calculations, or partial to no credit will be given. This is not a difficult lab. I don't think my instructions are that difficult. In fact, I'm removing a lot of stuff that you guys don't actually have to do. And then, of course, with lab flow, there's some questions that I just don't like. Why don't I like them? Because I don't explain them anywhere. Your book also is a good book, but this book is pretty adjusted to being online the way that we are. And there's some things that it doesn't go into detail and explain. So I do my best to remove stuff that doesn't match your book to a point that I can, because I always want you to be able to reference back to your book on stuff. I do what I can, but sometimes not everything matches up, and that's just unfortunately the way it is. Here is a question I don't like. Which transition would correspond to the highest frequency of light emitted? So if it's high frequency, then that means it would be a lower wavelength. So let's take a look. 6 to 10, that's out. 2 to 6, that's out. 1 to 5, those are out. Why are those out? Because those are absorptions. They're going up in levels, not down. So immediately these 3 are out. This is emitted. Emitted is going from a higher level to a lower level, not absorption. So then we have N6, 6 to 3, this is an emission, and 4 to 1, this is an emission. Now the problem is there's better ways to calculate this, but your book didn't provide them. It did one little picture, but never really fully explained it and didn't give the calculations on how to do it. So there is a way to do this. And I'm going to give you an example of how to do this. I actually solved this with the calculation I'm going to show on the next slides. I'm giving you the answer, but you definitely, on the next slide, there is a problem. You should know those equations on how to do this. Anyways, here's the answer. This is a longer way to solve that problem. This problem does not exactly match up exactly, but it's the equation that you would use. Calculate the emission wavelength of the photon that is emitted when an electron in a hydrogen atom drops from fourth energy level to the third energy level. Is this photon in the visible range? So what's the difference here? Well, you have two of them here, so you would actually have to do two calculations with the same equation. And then once you get the wavelength, plug it into the wavelength times frequency, and equals c speed of light. You can solve for frequency, and then from there you can go to the electromagnetic radiation scale and determine which is higher in frequency than the other. It's a lot of work, but it's actually not that difficult. I solved this doing this problem this way. But this is more of a lab. I don't really want to spend another 10-20 minutes explaining how to do this. So I'm providing you the equation that you should know and become familiar with. Even though this question is not exact, I did it, I plugged it in. Now, you might see when you plug in this equation, you see that this is N1 and this is N2. They flip them here. They flip them because most of the time when you see this calculation, it's with a negative sign. So they get rid of the negative sign by just flipping these one over the other, and then you get rid of the negative side that way. So what am I saying? Well, you can continue on once you get the wavelength. You can solve for frequency by plugging this in. You can do it for both of these transition states, and then you can determine the frequency. So this is not impossible. It is a good question. It's something that you guys should definitely know how to do. But for the lab, I'm not expecting this to go this detail. And you're booked in and provide a different way to do it, which is a little easier. So I'm not even going to cover that other way. All right. There's 8 questions in the quiz, and 3 of them I just don't like. Here's another one. It has to do with safety, but they don't talk about safety anywhere. They talk about Bunsen burner, but they never really talk about this. So I'm giving you this question and one more. So 8 questions. If you get some of these, you'll be lucky. I just don't like that they ask for certain things, but then nowhere to be found unless you go back to the safety. But if you're taking a quiz, there's no heads up that there's safety questions in here. So that's why I'm giving these to you guys. Anyways, that's the end. This lab is not too bad. Hopefully it's easy. If you want to go over the Rydberg equation, you can always email me. We can set up a time to go over that to help you understand how to use that. And that's it. So have a good evening.